during the section, just speak up or type in the chat. Right, we start. I left my original note in my office, so I don't know where do we start. But remember, we start right before this problem. So this is where we start on page 5. It's just a review of derivative and calculus. Right. So what we've been doing is the substitution rule, and this one's no difference. So we should let something equal to u, and in this case we just do x plus 4. It's a little bit too bright. Let me adjust the color. Yeah, that's better. Okay, I'll let u equal to the 2x plus 4. And the substitution will have two components, u and dx. So to get dx, we find derivative to solve for dx. Just take derivative. Derivative of this is 3. And I can multiply the dx over. And then divide by 3. So we have two components, u and dx. Next, this one has the limit of x. Originally, it goes from -1, now go to 2, -1 to 2. So we make this substitution. Originally, it goes from -1 to 2. So I will put in for x 2 here, 3 times 2 plus 4, that will be 10. And -1 in here, -3 plus 4 is 1. So x go from -1 to 2. U will go from 1 to 10. Okay. With that, we substitute into the integration. Now the limit from -1 to 2 now go from 1 to 10. That's limit for u. And we have e. The 2x plus 4, that is u. And dx is du over 3. So we substitute for dx, substitute for u, and change the limits. The 3 here, bring outside, and we have 3 stay at the bottom, from 1 to 10, e to the u, du. Of course, we have to put something there on the top to have a fraction. Default should be 1. Right, so we have that. And now just integrate e to the u. Integral of e to the u is still e to the u. And then we go from 1 to 10. I'll just substitute the upper limit, lower limit, and subtract them. So we just have 1/3 e to the 10. And now subtract, put in 1. And e to the first power is itself, so this is just e. we just have that. So that is the standard substitution problem. Okay. Now, go to this one. Now this is a little bit different than what you see on other problem. So first, you see that if we let u equal to cosine of x minus 1, the bottom, then we have du. So let me have a scratch paper. Don't write this down. Just put that on scratch paper. Now if we let u equal to cosine of x minus 1, and then we take the derivative, and there comes the negative sine x. Now, after if you go ahead and solve it, you have du over negative sine x equal to dx. And if we substitute in the problem, we have 1 over u, and dx is this, and that is the major problem, because we're not supposed to have this. So the substitution, if it works out perfectly, we should not have an x left, and we have an x in the integral of u. So that's why it doesn't work this way. So we cannot let u equal to cosine of x minus 1. We have to use something else. So what's that something else look like? It's not going to be any form of substitution. So we have to try something else, a little bit clever. So a few tricks. The toolbox in calculus 1 is that we can use factoring. I mean, just in algebra, factoring, completing square, those kind of things. This one we don't have that. But the point here is, it would be nice if we have this. I'll just give some example here. Let's say we have this problem. It will be a lot easier if we just split this into 2. So that case we suddenly a lot more doable. As if I flip the problem backward. Now that's a lot more difficult. Simply, I can split the top, but I cannot split the bottom. So the key here, the problem that makes this difficult is we have the bottom cosine of x minus 1 that have 2 terms. If it's just one term, the top may be more complicated. Doesn't matter. We can split the top, but can never split the bottom. So the point here, we try to get this into one term. That would be nice. Okay. So the motivation is we get one term at the bottom. And the trick for that is, remember some common things in algebra. Completing square, factoring. This one is multiply by the conjugate. You'll see why we do this in a minute. But the trick for this one is that we multiply by something top and bottom. And when it multiplies out, it becomes one term. And we'll see why we do that in a minute. But what we do is we multiply cosine of x plus 1. Top and bottom. And let's say, why do we do that? Well, the point here is we try to get one term at the bottom. So in that case, just multiply the bottom. The top will be just cosine of x plus 1. Not worry too much what we have on the top, but the bottom. Okay. Cosine of x times cosine of x. I just multiply it out. Cosine square plus cosine x minus cosine x and minus 1. Okay. the top I will have cosine of x minus 1, cosine of x plus 1, sorry. The bottom, this cancels out. We have cosine square minus 1. Alright. And then you say, wait a minute, there's still two terms. How did that help? Well, it's cosine square. So that helped. Because almost 90%, just 90%, not all. Usually when we have cosine square, we use P-town identity where the sine square plus cosine square is 1. We use that a lot. Of course, if we don't use that formula, then we have power reducing, which is another story. But for now, cosine square plus sine square is 1. Will that help? Here we have cosine square minus 1. So I will subtract the sine square on both sides and subtract 1 on both sides. So that gives us cosine square, sine cancel, that minus 1, 1 cancel, that minus sine. So this becomes just one term of negative sine square of x. And that that helps a lot. It is one term, so we can split the top. So that becomes cosine of x over sine x, sine square x. There's a negative. And now we have 1 over sine. Okay. Now, what is 1 over sine square and what is this? Now, just want to review a little bit sidetrack here. Review a little bit of trigonometry. Well, that's good. This is in this video, so if you watch this video, then this is a good review. Again, trigonometry, not calculus. Okay, so what I'll do is around a hexagon here, hexagon like this. Okay, that's more like a hexagon. Okay, so this hexagon, I have tangent here, followed by sine and cosine. Opposite from tangent is cotangent. Opposite from sine is cosecant. Opposite for cosine is secant. And then we have 1 in the middle. Okay, so that is a hexagon. So how did that help? Okay, actually, the hexagon, we have this symbol. That so this hexagon, is like majority of trigonometry we need for calculus is in this hexagon. So first one we say, if we have tangent on the top, there will be 3 ratio that follows. If tangent on the top, there's sine over cosine, 1 over cotangent, and secant over cosecant. So we can write tangent is sine over cosine, 1 over cotangent, or secant over cosecant. Right, that's nice. Actually, you can rotate. Let's say if I have cosine on the top at the 12 o'clock, so okay, 12 o'clock, cosine on top, then I will have 3 ratio. Cosine is equal to cotangent over cosecant, 1 over secant, and sine over tangent. So whatever function at the 12 o'clock, there will be 3 ratio, 1, 2, and 3, like that. So that take care of the quotient identity. Any function at the 12 o'clock is equal to 3 ratio from that hexagon. Okay, so that's number 1, quotient identity. Next, of course, with that, sine is 1 over cosecant, or cosecant is 1 over sine. That's simple. Next, the product. Any function is the product of 2 functions next to it. So tangent is secant times sine. Sine is tangent cosine. Cotangent is cosecant times cosine. Whatever the function is, it is the product of the 2 functions next to it. And finally, we have this symbol, and that is the Pythagorean identity. Cosine square plus sine square equal to 1. 1 square plus tangent square equal to secant square, and cotangent square plus 1 square equal cosecant square. So we have 3 Pythagorean identity from this as well. As mentioned, that the majority of trigonometry we need in this class come from that hexagon, so it will come in handy. Now back to this, we have 1 over sine. 1 over sine is cosecant, so that's nice. Okay, but before we do that, I just want to rewrite this a little bit. There's a negative cosine over sine. They'll say, wait a minute, that was sine square, right? Well, this sine x already need 1 more. So that's your sine square. Okay, I have to put 1 here. Okay, so that cosine is cosine and times 1. The bottom is sine times sine. Split like that. Now we have 1 over sine square. And then times 1 over sine x. Let's just make it a square like this. Okay. Cosine over sine is cotangent. 1 over sine is cosecant. And that is cosecant square. Right. And then finally, I'll ask you, what is the integral of cosecant cotangent, and what is integral cosecant? Well, if you go to I didn't print out that page, but the page where there is all the integral cosecant where is negative cotangent, and integral of this is negative cosecant. So bottom line is when it's all said and done, this equal to negative. Okay, integral cosecant cotangent is you can look on the page of integral that gives us cosecant. I'm sorry, negative cosecant. Integral of that is negative cosecant, and integral of this is negative cotangent. So we just have cosecant plus cotangent. So this problem doesn't have any substitution, because substitution will not work if the problem remaining have an x in the problem like this. It will not work. Okay. So this problem considered to be a classic problem, and the classic solution is to multiply by the conjugate. Right. This next problem a little bit different. Integral of 3x over square root of x minus 1 dx. Okay. So let's try substitution. Actually, on this one, substitution will work with a little adjustment. So let's say, obviously, we're not going to let u equal to 3x. We're going to let u equal to just x minus 1 here. And might be able to do something with it later. Okay, u equal to x minus 1. And we take derivative. Because we need to solve for dx. Derivative will be just 1 move the dx over. Right, so du is equal to dx. Simple enough. Right. Now the integral. This will be equal to there's still 3x on top. Cannot do anything with it. Square root still. X minus 1 is going to be u. Dx or just du. So that's good. The problem has one term at the bottom. So that's good. Like I said, 2 terms at the bottom cannot split. 1 term can split the top. So that's nice. What's not nice is we still have an x. That's not supposed to be. Substitution. If we let u equal to something, after the substitution, we should only have u in it. There's an x there. So that is the problem. So we have to take care of this. Luckily, this problem is not so bad. Because if we have u is equal to x minus 1, if we plus 1 on both sides, from that, we plus 1 both sides. You have x equal to u plus 1. So u plus 1 equal to x. I will substitute u plus 1 there. So sometimes the substitution will have x in it if we can solve for it. In terms of u, that's a lot more doable because everything in terms of u. And also there's 1 term at the bottom, so we can split the top. Okay. Before we do that, square root of u is like u to the 1/2. So I multiply it out on top. 3u plus 3 over u to the 1/2. And then we can split the top. 3u over u to the 1/2 plus 3 over u to the 1/2. Okay. Now reduce. We have 3 u over u to the 1/2. By default, it is to the first power. Divide, we subtract the exponent. 1 minus 1/2 is negative 1/2. Sorry, positive 1/2. 1 minus 1/2 is 1/2. And this from the bottom move to the top. That is negative 1/2. Yeah. So we split the bottom. Split the top, and we have 2 terms. It's easy. So the bottom need to be 1 term like this. Okay. It's easy. Integral, that will be 3. Integral of that is u to the 3/2 over 3/2. and then u to the 1/2 over 1/2. Divide fraction is multiply reciprocal, so we have 3/2, so that's 2/3. 1/2 be 2 over 1, increase, that's just 1/2. Okay, and that gives us 3 and 3 cancel out, that's 2 u to the 3/2 and 6 u to the 1/2 plus c, and u is x plus x minus 1 to the 3/2 plus 6 x minus 1 to the 1/2 plus c. Right. By the way, if you have any question, please type in the chat, raise your hand or just speak up. Right. So with that, we finish the. Oh wait. Yeah. With that, we finish the review section on Calculus 1. Now this is actually in Calculus 1 as well, but just want to briefly do this, because this is important in Cal 2, especially in chapter 8. Right. Just a second, let me put a calculator real quick. Okay, give me a minute. Okay, so we have a calculator. Okay, let's put that right here. Okay, just want to graph the sine function, really. Okay, so you have sine x. Okay, sorry, y equal to sine x. Okay, so that's just a wave. Now what we're interested in is the inverse function. The inverse function, if a function go from x to y, inverse function will go from y to x. Now the problem with the sine x is that just keep going up and down. Let's say for the y values of 1, there are multiple x values equal to 1, 1, 2, and 3. So that are on the graph here. So for 1 values of y, let's say 1, there are multiple values of x. Now that's not good, because the inverse function 1x, 1y, if there's 1y and there are too many x's, we don't have an inverse function. So we need 1x, 1y. So the way to do that is we have to restrict that. So in that case, in particular, if x, I could say from negative pi over 2, and y will be pi over 2. Okay, let's say y will go from, I just change the windows. Okay, so I will string out the domain for x will be negative 2 over 2, negative pi over 2 and pi over 2. Now let's see the graph. Now if the function goes like this, you have 1 x values for 1 y values. So that's why we have to restrict the domain so that it will be 1 to 1, 1x, 1y. The function will go from x to y, inverse will go from y to x. Bottom line is, just want to summarize all of this information onto this table here. Now, the sine inverse, we want to be just like that. And the domain, I'm just going to copy all of this. It's from sine cosine. It's a wave, so it is between 1 and negative 1. So these two will have the same domain. So if we draw a line, it will be between negative 1 and 1 for the domain. So we've said that is the domain for inverse sine cosine. Wait, is there a problem with the video, right? We don't see anything. Oh, yeah. Okay. I wrote something on the screen. Okay, let's try that. Okay, let me unplug the camera. Okay. Okay, so it worked. So what we try to do is try to summarize this information to this table here, and show the sine and cosine. The graph is the wave, so that's between negative 1 and 1 for both of them. Tangent and cotangent. Tangent and cotangent. The graph of tangent is this. So pretty much y can be any values. So the domain will be every values. So the whole numbers here. So for tangent inverse and cotangent inverse, we use different color here. All real numbers. All real numbers. And cosecant and cosecant, secant and cosecant inverse. Will be outside of negative 1 and 1. So be here. And here. So I will write negative infinity to negative 1, and then from 1 to infinity. Okay, keep this in mind. So just want to do this quickly. Also, this is trigonometry and it's not related to calculus. So trigonometry, let's use the semicircle, unit circle approach. So need a circle. Okay. So that's a circle. Yeah, you might see this in trigonometry already. Okay, unit circle. So the radius is 1. Now this will go back to the definition of trigonometry, and I'll explain why do we have the name sine, cosine, tangent, sine, tangent, and secant. Okay, so we have this unit circle. So we define a point. Let's say there's a point here. It has the x coordinate and the y coordinate. This is the y values and the x values. Of course, and then you say, okay, y value is sine and x value is cosine. That's the definition, right? Y equal to sine of an angle here is y. And this why do we call sine? Okay, so trigonometry is the subject that go back I could say about 5,000 years or even older. So all of that, the name translate from could be Egyptian, Greek, or Babylonian. But when it's translated to, I think, Greek, the sine, what we mean is the word sine meaning half of a core. So what does that mean? Let's say we have a bow, and then the string is called the core of the bow. So this is a core of a bow. And the sine, I think in Greek or some language, meaning half a core. So if you cut that in half of a core, and that coincides with sine, and sine is meaning that half a core. Okay, so that's why the name sine come from. And after that, there's the tangent. Tangent, of course, is the line tangent to the unit circle. So the line tangent will be this line. And this values from the tangent line to the unit circle. This values is tangent. Okay, if you don't, if you're not sure why is that, well, tangent is opposite over adjacent, right? So tangent is opposite over adjacent, which is good. And also, if we talk about the big triangle, right triangle here, opposite over adjacent. So that's why it's tangent over 1. Okay. And then, so tangent meaning touch. The Greek letter tangent mean touch. And the secant is this line here. Secant in Greek, I think, mean touch, mean cut. So we cut the circle, and whatever this distance is, the distance from the center to the tangent line, that is the secant of an angle. Now, of course, you can see that 1 square plus tangent square is secant square. So that work out. And then with that, we have x is cosine, and you draw this line, you have cosine, and you have cotangent and cosecant. But that's what the name coming from. Now with that, so that's just the name of things. Secant, the name secant, tangent, and sine, those where those come from. Now with that, whatever the point on the circle is, the sine cosine is the y and the x values. The y and the x values cannot be more than 1 because that distance x and that distance y cannot be more than 1, cannot be less than -1. So that's why we have this values. Now tangent, just because it intersect the point, we have the tangent values here. The tangent could be any values on that line. This point, okay, that we have that point here, okay, this. So pretty much tangent values can be anything on the line. So that's why we have from -infinity to infinity for tangent. And finally, secant and cosecant. Secant and cosecant is this. Because the point is on the tangent line, it is always outside of a circle. If it is outside the circle, that distance has to be bigger than 1, right? Yeah, so if we have this line, that secant bigger than 1. The smallest it is will be right here. That secant is equal to 1. So, but it is from 1 and up. Of course, could be less than -1 as well. So that's why secant and cosecant will be from 1 to infinity and from -infinity to -1. Okay, so that is this. And finally, the range for this inverse function. So for sine, tangent, and secant, those will be the same. So first we see -π/2 and π/2. So what quadrant is that? So we have -π/2 whole to π/2. And you see this is quadrant 1 and this is quadrant 4. So sine inverse, it is quadrant 1 and quadrant 4. -π/2 to π/2. Or we say Q1, quadrant 1 and quadrant 4. Okay. And cosine be from 0 to pi, but that easier. That will be, sorry, it's red here. 0 to pi, and this is quadrant 1 and quadrant 2. Tangent inverse. Tangent inverse will be just like this. The only difference is that they don't have the equal sign. As you see, if I have the point that on the infinity, then you draw it pretty much parallel to this, and so this line will go this. When it go parallel, it will not touch this tangent line. So when it's π/2 or -π/2, it will not touch this tangent line. So tangent does not exist. So pretty much this, but without the boundary. So we go from -π/2 to π/2. Pretty much Q1 and Q4, but no endpoint. Now, cotangent inverse, pretty much like this. It go from 0 to pi, and again Q1, Q2, no endpoint. And now cosecant and cosecant inverse will be just like that, quadrant 1 and quadrant 4 and quadrant 1, quadrant 2. The cosecant will be just like, because cosecant is 1 over sine, so it will be very similar to this. But so I go with -π/2 to 0 and then 0 to pi over 2. So pretty much just quant 1, quant 2, but without the endpoint. So pi over 2 to negative pi over 2 without the point in the middle. So Q1, Q4, no midpoint. And the other one is 0 to pi over 2. And pi over 2 to pi, Q1 and Q2, no midpoint. Okay, so that just summarizes what we have on that chart and a little bit of review of trigonometry. Most importantly, you have to be able to do this kind of trick. Okay. So suppose theta is equal to sine inverse of 2/5. What is cosine? You can say that cosine square plus sine square equal to 1. But yeah, that certainly works. But this trick you see again in chapter 8. Okay. So let's start with sine is equal to sine inverse of 2/5. Okay. And now what I do is to get rid of sine inverse, I can do the sine on both sides. So take the sine on both sides. And sine inverse cancel out. Okay, so we have that. And then okay, we have sine. Now how do we get cosine? Well, actually that's very easy now. If we draw a triangle. Now this trick we will see again a few more times. Okay, what is the ratio for sine? And you say, okay, ratio for sine is opposite over hypotenuse. So this triangle, opposite is going to be 2 and hypotenuse is 5. With that, we can solve for the adjacent using Pythagorean theorem. Adjacent square plus 2 square is 5 square. So adjacent square, this is 4, 25, so adjacent square is 25 minus 4 will be 21, and adjacent will be square root of 21. And with that, we have cosine of theta is adjacent over hypotenuse. Adjacent is square of 21 over hypotenuse is 5. So that's how we do this. So this common trick you'll see again in the future problem. Okay, let's do one more before we take a little break. this one. Cotangent of cosine inverse of x over 4. Now we can see that inside here, if we let that be theta, let's see. So theta is equal to cosine inverse, because any trig inverse is going to give us an angle. So let's call that theta. Okay, and the problem will ask for just cosine of theta. So cosine of cosine inverse of x over 4 is just cosine of theta. Oh, that's easy. Cosine adjacent. Sorry, cotangent, right? Sorry, cotangent. Cotangent is adjacent over hypotenuse. I'm sorry, adjacent over opposite. Okay, so with that. Okay, so theta, if we take the cosine on both sides, that gives us what? Cosine is equal to x over 4. Cosine is adjacent over hypotenuse. And we draw a triangle. Adjacent x over hypotenuse 4. With that we can compute the opposite. So the opposite square plus x square equal to 4 square. So opposite is equal to 4 square minus x square. And that is the opposite. And cotangent of theta, cotangent is adjacent of opposite. So with that, cotangent of cosine inverse of x over 4 equal to adjacent x over opposite square root of 4 square minus x square. 16 minus x square. Right. So let's take about 5-minute break. It's not a school, so we take a shorter break. We continue at noon, exactly noon. I'll pause the video now. Okay. So now we have derivative of inverse trigonometric function. So that will be the formula. If you memorize the formula, oh, good. But there's another way to find derivative of this without the formula. So what I do is I probably about 60% of the page and then 40% of the page I divide like that. Right, do on the 60% of the page over here. Right, so we have sine inverse. So what if we do sine inverse to undo the sine inverse, to cancel it, I will take the sine on both sides. We have that sine sine inverse cancel out. We have sine of y equal to x squared plus 4. Now I can write as x squared plus 4 over 1. Right. So the reason why I write x squared plus 4 over 1. Okay, actually we'll do that later. But x squared plus 4 for now. That will come in just a bit later. Now, from here, if we take derivative with respect to x on both sides, so differentiate with respect to x on both sides. Derivative of x squared plus 4, that's 2x, that's easy. On the right hand side, derivative of sine is going to be cosine. Now, remember we take derivative with respect to x. Here's y, and we assume that y is a function of x, so it's not like that. We have to have y prime or dy by dx. Just say y prime. Pretty much. Derivative is just going to be derivative in terms of y and then y prime. That's the chain rule. Because y is a function of x, we're going to have that. And now with that we can divide by cosine on both sides. So y prime is equal to 2x over cosine of y. The only thing need to determine is what is cosine of y. And for that, we get back to this. Draw the triangle. Actually, now the angle is going to be y, not even theta. Y. Sine is opposite over hypotenuse. So with that, the adjacent is equal to square root of 1 square minus this 1 square. So that's the adjacent. And therefore cosine is adjacent over hypotenuse. Adjacent, this over hypotenuse is 1. So that is cosine. Cosine is the square root of that. And substitute in here, so it will be just 2x over that one. So be mindful when we take derivative. This is with respect to x, so this have to be the y prime. So this is implicit differentiation that we learned in Cal 1. So that's nice and all. We don't have to memorize much in that. But if we just use the chain rule with that formula, if we have this, by the way, when we're taking the test, you have the formula with that formula. So it's not so bad. And if we just use that formula, y equal to sine inverse of x squared plus 4. Now derivative according to that is going to be 1 over square root of 1 minus a parentheses square derivative of the parentheses. So that is the chain rule. Derivative of that, and then derivative of the variable x squared plus 4, x squared plus 4. Derivative of this is just 2x. And that is 2x. And multiply that on the top. We have 2x and 1 minus x squared plus 4 square, because that is exactly like we have there. Okay, so if you have the formula, we just use that. If you don't want to use a formula, use that trick. And this one using the formula would be very nice. This one is not, a little bit more complicated. Alright, so in this one, if we want to take the same function to cancel inverse on both sides like what we have here, it will be different. So we will take the cotangent on both sides, but before that, we have to divide by -2. So we have -1/2 of y. Yeah, that's what we have on the left side, equal to cotangent inverse. Cotangent inverse. Of 3x minus 5. Then we can take the cotangent on both sides to cancel with this. That cancel out. That cancel out. We just have 3x minus 5. Right. Now we take derivative. Derivative of cotangent is cosecant square, negative cosecant square, sorry. So take derivative or differentiate with respect to x on both sides. Derivative of cotangent is negative cosecant square. But now, just like what we have there, we have to take derivative of this, which is -1/2 of that. Derivative of this is just y prime. Okay. And derivative of 2x minus 5 is just 3. Negative, negative, that gives us 1/2 secant square of -1/2 y prime equal to 3. Okay. So with that, I continue here. So the y prime multiply the 2, so that would be 6 divided by secant square. Okay, secant square. And now we can draw a triangle using this. Cotangent is cotangent, by the way, the angle is -1/2 y. Cotangent is adjacent. Adjacent over opposite. With that, we have the hypotenuse 1 square plus 3x minus 5 square. Okay, and finally secant is secant is adjacent over hypotenuse. Sorry, secant is 1 over cosine. So secant is hypotenuse over opposite, which is 1 over cosine. sorry, secant. Secant is 1 over cosine adjacent over cotangent. So that will be cosecant. Sorry, derivative of cotangent is cosecant, negative cosecant square. So cosecant. Okay. Cosecant. So we need cosecant. Cosecant is hypotenuse over opposite 1. And now cosecant square, so this one square. So bottom line is we have y prime is equal to 6. Cosecant is this square, so square under the square root. Right. Sorry about this. Derivative of cotangent is negative cosecant square, and so with that we have this. Right. Now this one, if we use the formula, this will be a lot easier. Derivative cotangent inverse is negative 1 over something square, negative 1 over 1 plus something square, and derivative of that something. So we have 3x minus 5 and 3x minus 5. Okay, this is just 3. And now there's a negative 2 in front of it. So we have a negative 2 in front of it. Sorry. Okay, negative 2. And then negative in the formula. Okay, that. And then derivative of that. So negative, so that make it 2. Negative times negative. Derivative of that is just 3. So if we use the formula, this is directly that in 2 times 3 is 6, and of course that will be the same thing as if we do that directly here. Okay. So yeah, whether we do that using the triangle or we do that directly using the formulas. On the test you will be given this formula. So you might just want to do that directly. But make sure just in this case, if there's a negative 2 or something, that will be there. Okay. Now the integral. We spent a whole section of chapter 8 talking about this. So for now, we just say, okay, we use the formula. Alright, so first when we look at this, if it is a formula, make sure it is in the right form. And the form is this. So when we see this, we see the square root of a constant square minus a variable square. So this should be the sine inverse. So we're trying to look exactly like that. And then we can use a formula. So for that, to look exactly like that, we'll take the 4 outside. And then we have the integral. (25) I can write 5 square minus x squared dx. Now this looks exactly like that, right? The a is equal to 5. And the formula, the integral for that is equal to what? Sine inverse of x over a, x over a plus c. That's it. Oh, there's a 4 in front. There. Yeah. So there's a formula. Just make sure it is in the right form, and we can use it. Right. This one is a little bit different. So when we look at this, this is the plus, so this should be obvious that we're going to use this formula here. But we need to have 1 on the top, and we have to have a squared plus x squared. Okay, here goes. First, I can move the dx on the back. Okay. So that's good. But I do need to have a squared plus x squared, or x squared plus a squared, meaning x squared plus something. So I need to get rid of this 9. To get rid of that 9, just have to divide by 4. I'm sorry, divide by 9. 1 over 9 on the top, 1 over 9 at the bottom. Now just multiply. That gives us 1 over 9 on the top. The bottom 1 over 9 times this gives us x squared. So that's exactly what we need. The x squared plus, and then 4 over 9 dx. Now manipulate this a little bit further. The 1 over 9, bring it outside. Now we have x squared, and 4 over 9, we can write this as 2 over 3. Square. Now this looks exactly like that, where a is equal to 2/3. And the formula is said to be 1 over a tangent inverse of x over a. So ignore the 1, 9. Is 1 over a and then tangent inverse of x over a. Plus c, and multiply reciprocal. 1 over 9 times 3/2 tangent inverse. Again, divide, multiply reciprocal, and 3 and 9 cancel out. That will be 3 and 9 cancel, will be 1 over 6 tangent inverse 3x over 2 plus c. So at this stage, that's all we use. Get the formula and then use it. Okay. So that is section 7.5. So in this section we study about the L'Hopital rule, and try to do something else. Let's do some simple L'Hopital rule. So the classic problem is finding the limit. The L'Hopital rule we use to find the limit, not just any limit. Let's say the classic problem is sin x over x. So this is a classic L'Hopital rule problem. So try to find limit of this. So remember, L'Hopital rule we use to find limit, but not just any limit. The limit has to be in the indeterminate form. So in this particular, I'm sorry, this go to 0. So first is just substitute 0. So you have sine of 0 over 0. Sine of 0 equal to 1. Sine of 0 equal to 0, sorry. And 0 is 0. So what we have here is 0 over 0, which is indeterminate. And we can use the L'Hopital rule. And the L'Hopital rule say if we have indeterminate form, we can take the derivative of the top, derivative of the bottom. Derivative of the top, derivative of the bottom, 1. And then put 0 in, we have cosine of 0 is equal to 1. Okay, so that's the standard L'Hopital rule problem. Now, the thing is, it's not just number 0 over 0. If I ask you, if it's this, now this is, you can say, okay, that is 0 over 0, but the difference here is that number is always 0. The bottom is changing, approach to 0. This one, it is approaching to 0. So approaching to 0 over something approaching to 0. That's different than identically 0 divided by something approaching to 0. Just want to do that. So in this case, this is actually equal to 0. Because 0 over x, if x is not equal to 0, it's going to be 0. So 0, 0, 0 all the ways. And so it's approaching to 0. So that's different. This is not indeterminate form. So it's not the L'Hopital rule. Just want to mention that. Now in this case, what we have in car 1, let me just backtrack a bit. What we have in car 1 is the indeterminate form of 0 over 0, infinity over infinity, infinity minus infinity. So that's what we have in car 1. Those are the indeterminate form. In car 2, indeterminate forms of this 1 to infinity, 0 to 0, and infinity to 0. What they all have in common is that they have the form of power. Something power exponent, right? So different than this in car 1. Okay, so it is 1 to infinity. Now, I just want to say it. The difference of those two is okay, sorry. Okay. I mean this. That is not indeterminate because this is identically 1 raised to the x power raised to infinity. So this is not indeterminate. But this one is indeterminate. You say, what's different? Well, this one, as x go to infinity, this one go to 0, and the whole thing here go to 1. So that's the key. It goes to 1. It is not exactly equal to 1. That's different. Go to 1, it might get closer and closer to 1, but doesn't have to be exactly 1. So that's different. This is exactly equal to 1. This is go to 1. And this is go to 1, and the exponent go to infinity. So yes, this go to 1, this go to infinity. So that is the L'Hopital rule. And that is indeterminate form, and we can use the L'Hopital rule. And from here, we just take ln on both sides, and we go from there. Alright, I think I want to continue this next time in class instead of try to go over here, because this is a little bit more important. So I want to pick this up in class. So pretty much we done today. And like I said, the recorded video I will send to your email. So if you're here, you're good. If you're not here, then you might want to watch this video before class on Monday.